Okay, so we are squarely in the middle of the code generation part of our project. So we went over the front end where we parsed and type checked. And now the goal is to take this syntax tree that we have, and for each different kind of construct that's represented in that tree, apply some assembly language template to generate code that's going to be equivalent to our simple ST input program. Last time we went over functions and how they're implemented on the machine. And so you had a homework to draw out the call stack for factorial. So let me go over what that would, so questions on that in particular, any specific questions on it? Who would like to see me go over it? Okay, let's go over it. So let me give you the assignment here. So this was similar to what we did in class, and it was not necessary to have the exact, Intel x86, 64, System 5 ABI. You didn't have to do the real calling convention. I just wanted to go through the exercise of creating the stack and destroying it when the function is finished. Okay, so I'll assume you have the code in mind. It's a factorial function. So let me draw the stack here. So we're first calling factorial of 2. So I'll just label this stack frame to keep us aware of which part of memory we're working on. So the stack frame for factorial of 2 will have a slot for x, the parameter that's in. This will be 2, so that's parameters. The return address here, I said we could just use the name of the function, so I'll just assume we're calling from main, or I probably didn't well specify this, but I'm assuming what's implicit here is that factorial of 2 is being called by something. So let's just say it's being called by main. And a pointer to the caller stack frame. So this would be pointing to whatever the calling frame is. If you put the main, that's fine. If you didn't put that, that's okay. It'll be more relevant when we actually do the recursive call, and you can see how this points to factorial, the call to factorial of 2. And any local variables. So here we have one local variable, new x. And in the C world, it's undefined to use an uninitialized value, so we can just leave its value empty until it actually gets assigned. Okay, so this is the initial setup for this stack frame for factorial of 2. And when this goes to execute the function, we know the value of x because we can look it up in our symbol table, in our stack frame. And our stack frame has the value 2 for x. So we substitute 2 for x here. This condition check fails, so we move on to the else branch. And here we assign new x. And to do that, we evaluate the right-hand side. In order to evaluate x, we look it up in our symbol table, it's 2. And then in your actual compiler, which we'll look at today, will actually generate assembly code that will execute the subtraction. And so this will compute 2 minus 1 and give us 1 for new x. And now, in order to compute the return value, we'll get the value of x, which is still 2, looking up at our stack frame. And then we'll compute the value of this sub-expression, but this is a function call. So in order to compute the value of this function call, we use in the machine level, we'll generate a new stack frame, effectively creating a fresh copy of this entire function for a new parameter. And so here's creating the new stack frame. So we'll interrupt the execution of factorial of 2 in order to compute factorial of 1. And notice that all of the state that we need in order to finish computing factorial of 2 is still retained here in memory in the caller stack frame. So we set up this new stack frame for factorial of 1, and it gets its own copy of x, which in this case is 1. Its return address, to simplify this, we'll just say it's returning to factorial, but when we go look at how the machine works, the machine will actually store the address of the next instruction in the caller function. And I can show, I show that looks like in GDE last time, although I think everyone's getting tired at that point. I'll go over it again, the way that works in the machine. But conceptually, it's just storing an address to some instruction inside a factorial. Then our parameters, return address, pointer to the caller stack frame. So you can think of this like, it's basically like a linked list. It's just storing the memory address that points to this stack frame. And I'll go over the Intel ABI again for one convention of how this works. But this is just going to be a memory address that points to somewhere else in memory. Excuse me. And our local variables. So we have new x again. Okay, and once we've set up this stack frame, we can begin executing this new version of factorial of 1, while the state for the previous call is held in memory. So here x is 1. We can look it up in our stack frame to see that x is 1 for factorial of 1. So this condition is true, and then we return 1. So there's several different conventions for doing this. In the Intel x86-64 convention that we have, it's stored in a register. Some other conventions actually store this value in the stack. But this resulting value 1 is, go ahead. Yeah. Oh, yeah, I mean, this factorial of 1 also stopped at the base case. So you could certainly attempt to, optimize that away automatically. The tricky part is determining you'd need some information at runtime to know which local variables are needed for which input parameters. It's like, but this is the same case. I mean, at runtime, you technically don't need space for new x, but in order to know that, so it's the same function. So if we have the same code for the same function, we'd have to add some additional code in that function to do some checking of the input parameters. You could certainly do that. That's certainly possible. I like things to be easy, so I like to do the same thing for every instance of it. It makes it easier to implement. But yeah, you could certainly imagine some optimizations to reduce memory usage or reduce the number of instructions that you have to run. Okay, so this creates a return value. We can think of this as either being on the stack or being passed in a register, but somehow there'll be some mechanism to take this resulting value 1 and communicate it back to the caller. So one kind of conceptual way to write this is to give a new memory treat it like a local variable, the call to factorial of 1, and assign it to 1. It works actually a little differently in the machine implementation, but just conceptually, this return value is being communicated back to the caller. And so now that once we've finished executing factorial of 1, so we've returned, we can use this information, use the return address and the pointer to the caller's frame in order to restore the state of the machine before we made the call to factorial of 1. So one way to think of this is that this stack frame will be popped off the stack, and we'll go back to running this function, this instance of the function. So here we were trying to compute factorial of 1, and now we've computed it, we know it's 1, and so we can finally finish this multiplication. 2 times 1, we get 2, and then we can set the return value here. I know I didn't mention return, like actually saving the return value in the stack, because in our calling convention it doesn't actually get stored. But it gets communicated back to whoever called factorial of 2. Questions on this? Yeah. Yeah. It depends on the calling convention. So in the x86-64 convention that's used for like Linux type machines, that's called the System 5 Application Binary Interface, ABI, it's the first 6 parameters are passed as registers and the rest are on the stack. So there's a finite number of registers. So if you have a function with like 1,000 parameters, which may be unusual, but it's feasible, you wouldn't be able to use registers always for that. The previous, I think the 32-bit one, everything was pushed onto the stack, and registers were not used for parameter passing, as far as I recall. Yeah, it depends on, it's just a convention. So if you're, it's just for interoperation with other library calls. So if you're not calling any other libraries, you don't want other people to call you, you can use whatever convention you like. Actually, you can, yeah. And you can optimize away parameters if you know, for instance, if they're not being used in the function, if you detect that, you can just avoid even passing them at all. You can even avoid the function call altogether and just copy the code in the caller function. But yeah, so it's just based on the convention, the calling convention. Questions on the function call behavior? So I think that's a good segue to, let's see, let me get the notes for today. So just to, did I show this last time? I showed this last time, right? The calling convention. So this is the calling convention that we'll be using, although I've left it as a bonus exercise to support multiple parameters, because it's a little tricky to get right. So for your project, which I'll go over today, you only need to use one register to pass parameters. But if you want to support this convention, this x86-64 System 5 convention, you would store the first 6 parameters in these registers here, and then push the rest of the parameters onto the stack for our function. So this function takes 8 parameters, A through H, and the first 6 go on registers, the remaining 2 go on the stack. And the return address is pushed, the pointer to the caller's frame is pushed onto the stack. And notice there's no return address on the stack here because it's, by convention, returned in an address. I'm sorry, they're returned in a register. And then local parameters are pushed onto the stack. So I'll go over a little more today. I mean, we actually looked at that last time. I went through the debugger to show you the convention actually working. And then I'll talk about today how to actually generate, write a compiler that will generate code to set up the stack frame for you. But the thing to keep in mind is that these local variables, when you're going to generate code for your expressions, for your function, the local variables are stored in memory in the stack frame. And so when we go to generate code, we're not going to know those values at compile time necessarily, but we'll know how to access them in memory through the stack frame. And so whenever we have a variable usage will generate code that will move that data out of the right spot in memory. And I'll show what that looks like today, I think in the second half of today's lecture. All right, questions on the general idea behind implementing functions at the machine level? And just, I guess, as a quick quiz, so why did we even bother doing this? Why did we bother having multiple copies of factorial's state? Or why do we even need to do that? Do we need to do that? What's the purpose of doing that? Couldn't we just branch? Couldn't we just jump and rerun the function? Yeah.
If we just loop the beginning function,
That's right. You would overwrite the caller's version of the variables, and you may get not what you expect. If your conception of the function is that it has its own local state, then this is at least one way to ensure that the function will behave like a function. Like each instance of the call will be its own computation with its own data. All right. So there's another thing I'd like to do today, which is to go over. So I've talked a little bit at the beginning about approaches to implementing code, approaches to implementing complicated projects that will make your life easier, that'll reduce the difficulty of debugging. And I realize with a lot of students coming to office hours, there's still some people who are coding, sometimes not even building, coding as much as they can, and then they have a nightmare debugging situation because they just have so much code that they have to debug all at once. And so I'd like to go over more concretely an example of the kind of approach I was trying to get across in the first lecture of the class, but actually show it in the context of the type checking project, which hopefully will help. I hope will help you as a coder and help see the philosophy that I use when I code, because I'm lazy. I want things to be easy. And so the way to do that is to basically put off coding for a little while. The temptation is to feel that if you're coding, you're making progress. But you actually may be building up, in the industry world, they call it technical debt. You may just be building up a bunch of pain for you in the future, a bunch of work for you in the future, feeling like you're making progress, but you're actually slower than you would have been if you had not coded at the beginning. This is like a tortoise versus the hare kind of analogy. The hare is just code, but then when you get to actually run it or build it, you have all these little errors to deal with while trying to deal with lots of complex errors. So the kind of tortoise method is one way to do the tortoise method is what I'm going to show you today. So this approach of code until all the coding is done, until you think all the coding is done, and then building, and then running it, and then testing it. This is called the waterfall model of software engineering. And who's heard of this? Who's heard of the waterfall model? You have heard of this. Have you heard of it as a good way to code? Yes? So the waterfall model is, I don't think it was ever a model of coding. I think it was, according to this, it was introduced by some academics as what not to do in coding. And the reason is, if you've ever tried to code hundreds of lines of code and then build and then test and run, you've encountered this, where now you have hundreds of lines of code, you have a bug, maybe one bug, but finding it is going to be a massive pain. And if a student comes to me and says, I have this bug, can you find it? I can't find it, I don't know. It's hard. It's hard to debug. So there's this kind of famous quote, among programming nerds from Brian Kernighan, one of the kind of original Unix AT&T guys, and it's this. Everyone knows that debugging is twice as hard as writing a program in the first place. By your experience, probably it's the case, right? Debugging's harder. So if you're as clever as you can be when you write it, how will you ever debug it? Or if you're as voluminous as you can be when you write code, how will you ever debug it? The coding part's arguably the easy part. The hard part is debugging and getting the code correct. And so there have emerged lots and lots of different ways to overcome this waterfall model mentality. It work, and the problem is in school it works for like really small programs. So if you're in CS1 or CS2, especially if you're quite clever and you're smart, then you can get away with this for a long time. And I know there's UCF undergrads are very good in computer science, and you can really get away with it for a while. But once you have to go to like 1,000-line programs, 10,000-line programs, 10 million line programs, I mean, no one is smart enough to keep all of that code in their head. As far as I know, I've never met anyone who could do that. And so at some point, you'll need to do something else besides just hold all the code in your head and just code. Especially if you're selling software and you have a client and they're like, hey, we want this little feature, can you add it? You gonna do another 10 million lines by yourself, or you need some other strategy to deal with all this code. And who wants to remember all this code? Do you really want to be keeping this in your mind a year later, all these millions of lines of code? So I'm going to show you one strategy today. There are tons of these different strategies for software engineering. And particularly since Nicholas Wirth, who's heard of Nicholas Wirth? Oh, not many. Okay, so he recently passed away. And he's kind of a luminary in computer science. A little shame that you haven't heard of him, but I'll introduce you to him now. He actually developed Pascal. Who's heard of Pascal? So as a teaching language, and wrote a well-known book on compiler implementation that actually other versions of this course used a version of that for the course. But he was highly influential, but you can see this stuff is probably well before all of our time. Probably no one here was born in 1971. But this is a really short, clear illustration of the kind of development that I'm trying to get across to you that will make your lives easier. And he does it in the context of solving the 8 queens problem. But you can really do this for any kind of code. And so I've linked this in the notes, so I strongly recommend reading it. It's very short and quite illuminating. Quite illuminating in how to do coding, or one way to do coding. So I'll summarize this quickly and then show you an example of doing this for the type checker. And then, hopefully you'll try to apply this in your coding. Yeah.
I figured everything out now, but some of you guys struggle with this assignment is that we practice drawing ASTs with declarations and stuff, but with something like a very specific example from check array expression, the only test cases I know are 100% right are the ones that you gave, and I feel like
Oh, I see.
just check array myself, I would look at AST and probably not know if it's completely right either way if I'm looking at it, except for obvious segfaults and stuff like that. But I think my biggest problem with bugs is my AST is missing information or there's extra information, but that's kind of I just went tried coding it all because I don't know what AST is supposed to look like except the ones that were given. Does that make sense?
I think so. And so, I understand. So testing, and actually we'll talk about testing in here as well. And I think if you follow this approach, it will. So this is kind of the age-old problem in coding, which is you have a specification of what it's supposed to do and you have your implementation. If you had a description that was so mechanically defined, that would effectively be your implementation. And so the challenge is, how do you map this kind of conceptual qualitative specification onto code? And one way to do that is with very thorough test suites. And so there's a notion of test-driven development where you just write all your tests and then make your code fit your tests. That kind of breaks down when you're dealing with the compiler because you have technically unbounded inputs. You don't have a small number of test cases. You have an infinite number of test cases technically. So you need some strategy to constructively prove that your program is right. Effectively by taking the specification and breaking it down into pieces. And by doing that, so I think your approach was, I'm walking a little blind here, so let me just run. And I'll just get by it really fast. And that's a way to kind of get homework done. But if you're coding I don't know, if you're coding like maybe airplane software, you probably don't want to do that. You probably want to stop and say, all right, what is the right specification here? And I don't know, this is a classroom project, it's not mission critical or something. But this approach will actually help reveal exactly where those missing pieces are. And then you can see, did I mess up? Did I leave something out? Or are the pieces actually there, but they're just too fine-grained for me to understand how they fit in the specification? And so the key to this is to actually break the specification down to the point where it's just before the code, and then you have a really tiny specification that there's probably some reference manual, which I think they're all here, that you can actually look up and find the piece of the implementation. Yeah?
I think that was what he was saying, is that it would be next to impossible to generate our own assembly test cases, because to get it to run, you need certain things to work. Like to even check if an array expression.
I see.
You need first to create an expression. That's you need first create a variable.
Oh, so the issue is that there's interdependencies between the functions.
You can't know if it's right until you're done. You can't really.
Okay, so I think I'll cover that here as well. So the trick there is to make a minimal test case that only exercises the code that you want to exercise. And that's hard to do, this is why I like the compiler. I know it's struggling, it's hard to do, but it's kind of the extreme of software engineering. It forces you to have to do these software engineering practices to get right. And so if you go out in the world and hopefully you're doing something less painful than a compiler, you'll be able to employ those, and then your job will be even easier. So the key here is to find the right minimal test case that only exercises the code that you've written already. And so I gave you code that works for a complete tiny program. So I basically gave you code that works for where are my test cases here? Yeah, this one. So, whoops. So I gave you enough code so that this works. I know it seems trivially simple, but starting from this, you can actually test one function at a time. And so the trick is to make a test case that only exercises that function. And so no amount of coding is going to help you know that. You can just write a print statement to confirm that you're in that function, and also confirm that you're not in any other places. And so it's a bit of a puzzle solving exercise, and I didn't give you all the exact steps to take, but you can figure out that, okay, if I do this function first, it involves no other code, and so you can just work on that function in isolation. It does also mean that, some functions do depend on each other, so if you get one wrong, it's gonna be tough. But then you can ask me or do a different function, or make your best guess about the specification. Yeah.
How do you recommend generic test cases where we know the answer? Because for an ASP, there's a lot of moving parts, and it would be hard to reverse engineer what a small test case would look like. But all we have is a big one.
Oh, okay. So there's a couple ways. There's a couple strategies to do this. So one is to just start deleting code from the test case. So you need some way to confirm your answer. So let's say we're trying to test whether it's hitting the functions that we want it to hit and not the function we don't want to hit. So you can just put a print statement in each function that you're concerned about, and then you just edit the test case down until it doesn't hit those functions anymore. So you know what I'm saying? So effectively you need ground truth, right? That's the issue. You don't have ground truth. So you can make your own ground truth through testing. And I know you don't. So having ground truth for actually what it's supposed to be. You're supposed to be able to get it from my specification, my type checking specification. But again, might be a little loose. But what you can know is reachability. You can know reachability just by testing. So you can get ground truth yourself. The answer to, is this test case touching this part of the code? That's something you can do on your own without anyone telling you. You can just run the machine to tell you that. And so, I've given you some large test cases, but there's no rule saying you can't just cut this down and delete stuff until it only touches the code you're working on. Does that answer your question? I mean, I guess you still don't have ground truth for that cut down case. Is that the issue?
How do you know? Okay, I made a really simple test case, but how do I even know I learned this correct output? Because I have nothing to compare to.
So I guess my expectation was that looking at the type specification, you'd be able to figure it out. But maybe I'm taking that for granted a bit too much.
That might be a bit hard because like, how do you know each of the levels in the tree is not correctly? Because it'd be hard to look at a tree and build.
I see. Yeah, I guess the best thing would be to have an oracle that tells you, like I give you a compiled program already, and then you can run it and get the right answer. Yeah, I mean, I think at least you can make a best judgment about what the answer should be. And then if you get it wrong, you can just tell me, hey, that's what I thought it should be. And I'm not going to take you points off for that, especially if it was a gap in my specification. So this is more like a pedagogical thing. Like, so what's the right way to convey? Because all this stuff is mechanical. And so the best description is the one that just runs on the machine to me. So, but I don't want to just give you the code. I want you to do some experience of coding. But yeah, I understand that's tricky. I was sort of hoping to be able to figure out the type tree based on the rules. But I understand that's hard. Okay, but let me go through an example of this stepwise refinement approach. This program development stepwise refinement, at least as I see it, on the type checker. Hopefully this will. Well, I don't know. Maybe this will help. I'm not sure if this will help with ground truth, but hopefully it'll at least help reducing where the lack of knowledge about ground truth is to a really specific part of the specification, instead of just a big program and not knowing what the final AST should be. Okay, so just the approach in a nutshell is to take your general specification and break it down into a series of steps. Not programming steps, but break it down into a series of steps. Then, if those steps are also, you're not unsure about how to implement it, break it down into even smaller steps. Until you get to a point to where basically one step is like one line of code, or at least something you can look up. So for instance, if you're trying to say, sort a file, well, how would you do that in C? Well, you need to open the file. So, okay, you got to open the file, you got to read it in, you have to have some sort, you have to write it out. Well, now you have 4 steps. And some of those are easier, some of those are harder, but certainly doing each of those steps is easier than the whole problem. And so maybe reading in the file, you can go on Stack Overflow or go in the Unix reference manual and say, all right, how do I open a file? And you can get the code for that. And you can do that independently of all the other steps. That's kind of the key. So let me show this with the type checking project. All right, let me set this up. And okay, the function that I was going to do was, deref. Okay, so I've got my really basic test case here, and I have my empty unary expression function. So in the kind of stepwise refinement approach, we would take our specification. So I'll just go, and let's say I'm doing the deref operator. So I need to do these steps. I need to type check the operand, check the type of the operator, and use this to set the unary expression's type. So I'll just do this for dereference right now. So one trick that I do often when I'm coding is I'll write comments before I even write code. I'll write comments describing what I need to do, and then work on each of these separately and try to break the problem down. All right, so type checking the operand. In order to do that, there's a few steps we need to do in order to type check the operand. So first we need, spacing is annoying me, so. So there's a few things we need to be able to do here. We need to be able to actually get the operand. We need to be able to type check it. And we need to be able to get its type. So breaking the problem down into even smaller steps. So how can we get the operand, or what information do we need to use in order to get the operand of this? So we're passed in an expression subtree, and we know it's a unary expression because we're in the unary expression checker. So how can we get the operand of the expression, or where do we find the reference for the AST? Yeah. Yeah, an AST.h. So AST.h, and I know I wrote this so I'm more familiar with it, but if you search for the unary expression, you'll find the specification of all unary expression AST nodes. And so this gives us, there's only two children. One is the operator, and one is the expression. So in order to get the expression, this tells us where we can find it. And using this, I went over this anonymous union pattern in C. But if that's you may have not have seen this before, but you can see this used in other parts of the code, the example code I've given you. And the way to access this is to get the unary expression anonymous union, and to get the sub-expression, you just get the child expression. So this is something that you may not be able to generate on your own, but you can look at examples to say, all right, how do other expressions explore the AST? So I'm just going to leave this in comments here because it's just a little snippet of code that I found to get the operand. And so breaking it down this way, if you're uncertain about something, you can at least move on and work on other stuff. So even if you don't know how to do this, you can say, all right, well, I'm going to have some sub-expression. Let's say it's going to be, we can make a variable to kind of factor it out and say, well, okay, this is to do here. If you want to make it runnable, you could make it null or something, or give yourself big alerts to go fill this in later. But you could give yourself a little placeholder here before you even code it. You can give yourself already have some code that will at least build and run. Then we need to type check this. So how do we run the type checker for an expression in our type checker? Check expression, right? So we know we're going to have to call check expression on something. And you can even do this, you can even work backwards. You can say, all right, well, I'm going to check expression on the operand. I haven't defined operand yet. This isn't even real code. But you can start giving yourself like complete pieces of code before you've finished the whole function. So you can think of this as kind of working backwards, where I'm gonna call the type checker on some operand. I don't know how to get that yet, or I haven't written the code for that. But there's no law that says you can't like write that code. You can still write it if you want. And how do we get the type of expressions in our type checker? Does anyone remember, or everyone know where to find the information? Yeah, it's arrow type. So this is also described in the AST, and if you look at other example code, that's there. So we're going to have some operand, and this is how we're going to get its type. It's not clear yet where we're going to use it or how to store it, but now we've got the first step one, type check the operand. We have it broken down into several substeps, and we've identified some code that we think is going to be used to write this whole algorithm. So you can continue on like this with all the rest of the steps, or you can go deeper here and get this one piece working. It kind of doesn't matter whether you do breadth first or depth first. The main key is that you're breaking down the problem into separate steps so that it's easier to find the right code to implement those small steps and then putting them together. Questions on this? So when I'm doing like actual coding, I do this all the time. So I never know what the right implementation is. You never will. That's our job if you're a programmer, to write that implementation. But there's no rules about writing this top down. There's no rules that you have to have all the implementation done for every piece of it. And so you can just make functions that are empty and return a dummy value, or other tricks like this where you don't have to write all the code all at once. Okay, so so if I were actually coding this, I'd probably actually just finish this and then test it. You could also, you could try to do this, break things down more, find all the pieces. But at some point, you'll need to build and test this thing. So this comes to, how do we actually make a test case for this? So I made this language C-like in hopes that it would help you sort of know ground truth, because you hopefully are mostly familiar with C and probably are familiar with its type system, even if you don't exactly know its typing rules. I think intuitively I was hoping you'd be familiar with the behavior of C. So if we have, say, a pointer type, I can take our where was our simple case here? So I'm going to make a new copy of this, simple C, for my unary expression. And so just like with coding, there's no rule that says you have to use only the tests given to you. And I'd strongly recommend actually copying them and just making, even if you have 1 million test cases, that's better than just editing. Like one common, it feels easier to just edit the same file and then kill what you had before and then edit it. But it's no harder to just copy it. And then you're actually building up your own test suite, which in practice is what you need to do. You won't be given a test suite necessarily, unless maybe they're test engineers, but you're unlikely to be given all your possible test cases. So just build your own test suite as you go along. And notice that I've done no actual coding, right? I've just planned and now making test cases. So okay, so now I need to make a test case that's going to exercise only what I need to exercise in order to solve the problem I'm trying to work on here. So the most basic thing to confirm is that I'm actually have a test case that actually hits this function. This will solve you lots and lots of frustration. This is like the is it plugged in question. Somebody calls system like customer support and they're like, did you plug in your machine? These like classic viral videos. This is the is it plugged in question. And so my strategy is do the easy stuff first. Do the stuff, the low-hanging fruit first, because if you wait till later, you won't know if it's something simple or something complicated. So before we even get to coding this, we need to make sure we have a test case that actually just touches this. That's the most basic thing to confirm. Okay, so let me get this test case that I created. And so this is where knowledge of C and maybe a little trial and error is needed. So in our language, so in simple C, how do we declare, so we're doing a dereference, so what kind of variable do we need in order to test a dereference? We need a pointer, and so how do we declare a pointer in the language that I gave you? Who knows? I mean, you can look up existing test cases, you can look up the syntax of it, or you can ask a question. You can say, how do I declare a pointer? Does anyone know how to declare a pointer in simple C? Yeah. Pointer and angle brackets. So let's just do a pointer to an int. And now, assuming that you haven't written lots of code, you just have your basic implementation, I would actually test this. I would even little by little. I mean, I'm super paranoid about coding. I don't leave anything to second guess. I don't leave anything to chance. I say, all right, if you're writing this and just assuming it works, well, I'm very skeptical, so I'm going to actually test to make sure this works at this point, just so I'm not getting any simple stuff wrong. And so I get the AST, because I've given you the code to compute the AST. I don't get a syntax error, which means it's at least syntactically valid. And so now how do I do a dereference? It's just like in C, right? So I could do it here in the return expression. I could make a new variable, x, but somehow I need to make a statement that does a dereference. So just like in C, I can just assign x to be a dereference. Now this requires an assignment statement. So I won't go into, I'll assume that that's working correctly, but if you wanted to just make sure you're reaching through assignment statement, you could just do the minimum inside of assignment statement in order to execute the type checker for this sub-expression. Since, if you know how to do that, you can go to assignment statement and just do the minimum to make sure it reaches. But you'll know immediately whether your assignment statement is giving you enough information, because I'll see this reached here. And I'll have ground truth telling me that I'm reaching the unary expression. You won't be struggling with, is assignment statement written? Is it not written? So if I hadn't written assignment statement yet, let's say this was empty, then you would never see reached here. And so you'd be so that's why doing this, is it plugged in check first is really crucial, because you may be coding away inside of unary expression thinking something's not working there, when in fact it's something simpler. It's just not reaching this code. So I'm going to assume that assignment statement is at least calling enough of the type checker to reach unary expression. And by just putting this little print statement, I can confirm that indeed I'm reaching this code. So there's an error here. I mean, who cares? The code's not written yet. I'm just trying to check reachability right now. Okay, so I have code that if you know C and you can look at examples in simple C, you can be pretty sure is the correct, a valid input that actually tests our case. Now this does bring up the other question, which is, what's the right AST output for this? And this is where you can either look at an existing test case that type checks a pointer, or make a kind of educated guess that what this AST types, what the types on the AST will look like. And so you can just ask yourself, okay, if this is my expression, what is the type supposed to be of this expression? Like in C, what would the type of this expression be? An int, right? If you have a pointer to an int, you dereference it, you get an int. So I was kind of hoping you would kind of do it that way, but I may be giving you too much uncertainty. But anyway, if you break down the problem in this very specific way for a very specific case, then you have an extremely specific question. Rather than how do I write a type checker for all expressions, it's what should be the resulting type of this? And so if you're uncertain about that, yeah, you can ask, or if I didn't give you enough information, or you missed it in the documentation, then that's a very specific question with a really specific answer. And you can even annotate your test case to say, this result should be an int, so that way you have ground truth when you go to test it. You can use your best judgment, you can take a guess, but at least being specific about it will mean there's a very specific, easy fix to it if you got it wrong, rather than lots and lots of guesses together. Okay, so kind of taking for granted that you know what the type result of this will be, we now have a test case that will test unary expression, and we at least know that the result of this should be an int. What about for A? What should the result of type checking A be? What's its type? Yeah, pointer to an integer, right? Because we just declared it to be a pointer to an integer. And I think I gave you the code for getting the type of a variable usage. So you can hopefully assume that works, hopefully correctly. Okay, so we've confirmed that we're reaching this code. And now I'd like to do the first step. I'm going to actually code the first step before I move on, but you could also just break down the problem even more. But I'm going to code the first step here. So the first step is to what? Type check the operand. So what's the operand here in this expression? The operand. Or what's the operator? So in the unary expression here. So the asterisk is the operator. Which operator is it in this context? Dereference, like in C. And so what's the operand of this operation? A. A is the operand. Okay. And its type, as we said, we expect it to be pointer to int. Okay, so we need to type check that operand. We've already talked about how to actually get the operand here. So I will use this code to actually get the operand. And so you can if you're in doubt, you can use some print statements to confirm what this expression is. So in our test case here, which AST type do we expect A to be? And we can use our AST reference to help us, or the information from the first project, hopefully, to help us. So what kind of expression, so these are all the expressions, what kind of expression do we expect in this test case? What's that? Sorry, I can't say anything. Well, so for the sub-expression, for the operand of this, so this is this unary, and I would say look at the AST to help you piece out the pieces of this, and actually I can do that here. I have this fatal error, which I guess is stopping me. So you can just use, so a way to look at the AST is to just stop doing the type checker and print out the program. But you can do this with your first project, or take away all the code that's causing the type checker to fail, so that you can actually see the AST. So it might help to look at the AST. So here's our unary expression here. There's only one, because we designed this to only be a really small test case. So this is the AST and you can keep this handy for your test case to help you look through, explore the AST. So the first one is the operator, the second one is the sub-expression. And so this is probably a good thing to do as well. Take your test case, make the AST so you have a reference of it. And so what's the type of our operand here, or which expression type is it? Yeah. Oh, sorry, not type. AST node. AST type. Yeah, you're right. It's a pointer to an int. That's right. Type is an overloaded term. Sorry about that. Which kind of expression is this? Ident expression, right? So you can actually just run your test case with the AST if you want a concrete reference to this specific test case's AST. And so it's an ident expression, and we could actually use the AST, like we could actually just print this out. We could start printing out this stuff in this sub-expression. So, and you can do this step by step. So if you're unsure whether the sub-expression is an ident expression, you could print out its kind. If you're unsure, and so in C, it's a little harder to do this debugging because you have enums instead of clear values. But take all the C knowledge you have and do your best to have print statements. But we could print out the kind here. Oh, I'm thinking of a different language. So am I reaching? Oh, I'm not. So my reach statement isn't here. So I immediately know that I messed something up here. I didn't mess something up, but I changed my main method to turn off type checking. So reached here, and it's 0 is the kind of the AST. So enums started 0, which maybe this is detailed C knowledge. I'm not sure. I'm not sure how much this is taught to you, but there are ways you could confirm that it's an ident expression. For instance, by comparing it to, I think I can do is B bool. I don't remember. I can just leave it as D. So I can say compare it to the enum for ident expression, just to make sure that it is an ident expression as I expect. So it's true. It's 1. So anyway, my point is, at each step, be skeptical, or at least think of a way to confirm it. And if you can't think of a way, then break it down into a smaller piece and say, all right, well, how do I get down to the nuts and bolts to confirm that each step of this code is doing what it's supposed to do? And this is the tortoise versus hare problem, because that feels really hard and really slow. Feels very slow when you're doing it. But no one can write perfect code, especially when you're uncertain about what to write, which will be true in all code that you're doing. And so the remedy to that is to just break the problem down further until you get to a place that you have some ground truth that you can confirm and you can be very sure of. Or at least, if you're not sure of, it's an extremely specific question that you can ask someone and get an answer. Or a decision point that you can make a very clearly defined decision and clearly documented decision about what decision you made about it. So I'll leave you to explore the AST and confirm all of these pieces. But assuming that we've confirmed that this is indeed the A sub-expression, then we can move on and say, all right, at least for this test case, this is right. And because we broke this problem down from its specification, we can be pretty sure it's going to work for other test cases as well. But let's walk before we can run and make sure it works for this test case. Since we're building from the specification, we have some hope that it'll work for other inputs to this program. Okay, so I know that was a lot to get to one line of code, but I promise you that your coding will be faster overall for sufficiently complex and large coding. For small programs, yeah, you can hack through it. But for sufficiently large and complex programs, your output of code is going to be slow, but your output of correct code is going to be far, far faster than just code. All right, question so far. So we got to one line of code. And so now, I actually like testing each line of code. And so when we move on, we can be pretty sure that this is not going to be where the bug is. Pretty sure. At least higher certainty than if we had coded the whole thing altogether. And so now when we go on to do the next part, if there is a bug or if there's some issue that we don't expect, we can start at the part we're currently coding rather than looking through the whole program. Okay, so we already kind of came up with a code for checking it, but I gave a different variable here. So let's say I forgot to change the variable name. Well, when I go to build, I'm going to get this error, and I don't have to guess about where this error is because I just made a change to the code that broke my test. So I can be very, very certain that it's in this code that I'm working on. You see what I mean? So by really isolating, kind of like a surgeon putting a little circle in their sheet that they're working with to really isolate the problem you're working on. And it will feel slow because you're working at this very detailed level. But at the global level, it will be much, much faster because you just won't have to go back over your code over and over and over again. Okay, so I made this error. What's the fix? What did I do wrong here? What should I be type checking? Yeah. Sub-expression. I set up this this line of code. Another way to think of this is that each piece of code in your program provides an input and output guarantee. So the input guarantee here is that I have a unary expression in the expression variable, and the output guarantee is that I have the sub-expression in the sub-expression variable. So just like with a function, the function provides guarantees about what the inputs and outputs are. So when you call, say, a sort function, you'd never think to even bother debugging inside that sort function. You trust the person who gave it to you, and you trust that if you give it an unsorted array, it'll give you a sorted array as the output. And you can treat each line of code that way as well, and use that, your knowledge of what it's supposed to give you as a way to debug it. So that's why I was writing some tests here to say, all right, let me confirm that the output of this statement actually is the A ident expression subtree. Okay, so let's move on. So we've got this type checking part. Now let's build and run. So and I actually have code that will go inside check ident expression. So we're actually in check ident expression. And again, we could do confirmation here to make sure the output is what we expect. Part of that is getting the type of the output. Okay. So we already looked at how to get the type of the operand. Again, I have the same error where I used a different name. Okay, so this is how we get it. This is how we get the type. Now, we're not using it for anything yet, but it's nice to have that code there, and we can make sure it works. We can do all of our tests. So see, I even have some weird build error that I don't know. What? That was weird. Oh, I didn't save it. Okay, I don't know where that build error is coming from, but I can handle it before I move on. Yeah.
I think it wasn't like you just have the sub-expression error type just
By itself?
just by itself. I think it wasn't.
It should be okay. So you can, yeah. I mean, there's an expression statement in C, so you can literally just say like 1 by itself. This is legal C. I mean, it doesn't seem very useful, but it's just in the design of the language is that statements can be just an expression statement. Actually, assignments are statements, expressions as well, which is why that's possible. Okay, so we finished the first piece of what we need to do, which is to type check the operand. And I know it seems really long when I go through it, but I assure you that debugging this tiny piece of code the whole is greater than the sum of the parts here. Debugging 10 pieces of the code together is far, far greater than debugging each piece individually, even adding it up. You see what I mean? So the whole is more painful to debug than the parts are to debug in general for sufficiently complex and large code. Okay, and so because I put comments here, I can easily pop back up to the specification because I took that out of my head. I didn't have to think about it while I was doing the individual specific coding of that one piece, type checking the operand. And so just like with a function, I pushed that onto the stack, but I didn't use it in my mind. I pushed it here onto the page, so I didn't have to think about it anymore. It's all about reducing your kind of cognitive burden in coding. I know you may feel really smart, like coding really complex stuff, but I like being lazy and making things easy, and so the trick is to do this, use tricks to get the not have to remember things, get these things out of your head so that you can just focus on the specific thing you're working on in the moment. Okay, so we need to check the type of the operator. So here, the type of the operator is given to us. The dereference just takes the where did I have this? Oh, that's array. Okay, so this tells us what we already asked, what I already asked you guys, which is if A is a pointer type, then the resulting type of the whole expression is the type that's being pointed to. So how can we get the so we have the type of the subexpression. How can we get the type that it's pointing to? Or at least where's a reference we can look to in order to, once we have a type. So here we've got a type already. What's the reference we can look at for the structures of types? AST.h. AST.h has the type struct here. So now you can actually confirm that this is that struct if you wanted as well. I mean, you could set it to a type, but I'll just use this type expression. Okay, so we need to figure out how to get the type a pointer int is pointing to. So looking at our AST, so that's like, I mean that's the first thing we need to do. So let's find some code that will help do this. So first of all, how do we confirm that the type we have is a pointer type using our anonymous union style? Yeah. You look at the kind. So we could confirm it's a pointer by looking at the type's kind field. And so what will that look like? So we've got the type. How do we dereference the kind field? Just a classic struct dereference. So we've got the type. This is how you look at the kind field. And so how would we, what would we need to check it against to confirm it's a pointer type? Looking here. So here's our kind enum. What would we compare it to in order to check that it's a pointer type? Yeah, this enum here. And so without even like writing code, I can start pulling out pieces that I'm going to need in order to write this code. And to confirm it, this is just C coding. So this is how I can check this will run if it is a pointer type. So a good style that I also like to use is to, whenever you write an if statement, always put the else branch, even if it's empty. So this is not a pointer type. So I've given myself a little template to fill in with comments that will guide me on what I need to do next. Okay, so if it's not a pointer type, what does this tell us? If we're trying to dereference something that's not a pointer type, it's a type error. So this is a type error. Here, we just need to move on to the next step. So there's a couple strategies here. We could just leave this empty. And then just move on to the next step, which is saved here in our comments. And let's finish out the implementation of this checking whether it's a type error. So how do we check for, how do we trigger a type error? Or what's the reference we can look at to trigger a type error in the code that I gave you? Yeah. Yeah, there's a function type error. So I'm probably going to have to call type error with some message here. Okay, so this is code that will confirm that it's a pointer type and actually check the pointer type. And I can go to code it. So there's nothing to code for the if branch. I just leave it empty intentionally. There's There's no law saying that you have to have code inside of an if branch. It can be empty. And it's kind of beneficial to have it for a specification point of view because you can document exactly all of the behavior for each condition, even if the behavior is meant to be nothing. Otherwise, you can't tell the difference between incomplete code and code that is intentionally empty. Okay, so I need to have some type error here, not a pointer type. All right, so I've got a little more code. I'm gonna build. It builds, so I don't have to be struggling with build errors later on, and continue running on our test. Okay, so if there's no other output, if I don't have any debugging output, there's no other output I expect. Let's go on to the last piece here, which is to set the unary expression's type. Okay, so where's the code? So there's a couple things I need to do here. I need to know what's the variable holding the unary expression. How do I assign its type? And what type do I assign it to? So I'll break this piece down into several steps that I need to be able to solve. So for the unary expression, what variable in this function is holding that unary expression? What's that? So let's go back to our, so we could confirm that. So we could do some print statements and say, all right, is sub-expression a unary expression? And we could write some print statements, check the kind, and we'd find that no, it's not. It's actually an ident expression. Why is it an ident expression? Yeah. That's right, yeah, it was this sub-expression to the operand. So if we keep our code handy, if we had that question, we wanted to confirm it, we could print out that sub-expression variable and see, oh, okay, that's the ident expression. And then you'd immediately remember, oh, yeah, that's right, I was using that somewhere else. So you can always kind of make your own ground truth to do this. And so think of it as not guessing, think of it as hypothesis checking, where I say, all right, I think this is right, let me confirm that it's right. And if it's wrong, that should help lead you to the right answer. So no one can keep all this in their head successfully, as far as I understand, at least over days, weeks, or years. So use this approach of hypothesis checking. Okay, so we ruled out sub-expression. What other variable could it be? So if we look at our code, there's only two places where expressions are defined here. So it must be this. The unary expression must be here in expression. And you could write code to actually confirm that it is indeed this sub-expression. This, you could actually print it out too. I have a AST printer you could use to confirm that it is that one. So okay, so expression holds it. How do I assign the type of an expression? I just use the expression, the type field. So that's the kind of code I'm going to need. And what type do I assign to it? How do I know the type to assign to it? Thinking about the overall problem, what was the goal here? Yeah? Someone had an answer? Yeah, the type, the pointer type is pointing to. So in order to do that, I need the pointer type. So how do I get my pointer type? Where was the type of that sub-expression? So looking past in our code, we actually had this already in our comments. We can go back and remind ourselves that, okay, this is the pointer type here. So this was the pointer type. And then the question is how to get the type it's pointing to. So how do I do that? I can look at the reference, AST reference, to my type here. I've already confirmed that it's a pointer type, at least for my example. And so here is the data that's stored for the pointer type. Maybe the name is a little confusing. So it's like type that's being pointed to, maybe is a better way to say it. But this is the only thing that's available for the pointer type. This is the only data that's here in the subtree. And you could actually, you could look in your AST tree here to see the structure of the pointer type and see, okay, so that pointer type actually has this int type as its child. So the way to access this from the sub-expression, bless you, is just get the pointer type data field from the pointer type. Okay, so now we have the pieces that we need. We have the type we need to assign to, and we have the type to assign it to. So then we can try writing our code. All right, so I'm going to build and test. Oh, and now I don't get any more crashes. So if you had crashes, then go back and reconfirm what you expect the value to be. So I got lucky here that it didn't crash. So if you're confused looking for the tree, because we only made a very simple test case, there's only one unary expression here. You could grep for it, you could search for it. This is the unary expression. We can see this is the ident sub-expression. And this is the type of the unary expression. And so what type is it? It's an int. And going back to our actual test case, what is the type of the unary expression supposed to be? An int, right? So dereferencing and pointing to an int. And so sure, you don't have ground truth for this, but you can, I hope, reason it to some degree what it's supposed to be based on your knowledge of C and the type specification. Yeah?
Since our example was only looking at the dereferencing example, should we put the expression arrow type inside of the condition?
Yes, for sure. So this works for this one particular test case. But as soon as you start trying to work on other unary expressions, you'll quickly see that there are multiple kinds of unary expressions. So there's also a reference type. So how do we check? So this part of the spec. So I kind of skipped over this part of the specification, but this part here, this choice here. How can we check which operator we have? So first of all, let's see. Check which operator we have. So how can we check which operator? We can look at our AST and first figure out, all right, where is the operator for unary expression? So looking at our AST again, we get it through the op field. So I'm going to take for granted we know how to get the unary expression, but you can always confirm it. So this is how to get the operator. And you can either do this by looking at the parser or running test cases for different operators to figure out which enums are used for the operator. So it tells you here that it's an eop enum. The eop enum is defined here. So these are all the operators in the language. But in the specification, there's only four you have to deal with. So you just need to know the op names of the four you have to deal with. You can do that empirically by running tests. You can do that by looking at the parser. You can do that by guessing from the name here, like ref, deref, negation and logical negation and unary negation. So that will take a little puzzle solving. You can also ask questions, say like, I'm not sure which operator it is, and just leave that piece empty while working on other ones. So a kind of clever way to do this is to use a switch statement. So you can say, use a switch statement for this, and so we're doing a deref. Here's the deref operator. So this is put the code for deref here. Just like with if statements, I recommend always putting should never reach, or I recommend always putting something for the catch-all case. If you want to go be really, give yourself runtime feedback, you could even put print statements to tell you, to do, you haven't finished, or something went wrong. So anyway, yeah, go ahead. Yeah, you could. You could, but it's the parser should defend against this. The parser should not allow this to happen in the first place. Yeah.
I was going to say, because tell you what calls the unitary expression checks on,
That's true. Yeah. Yeah, it shouldn't happen. It should be defended against by the part. Yeah, it should be defended against, but you don't have to assume that. You can put a message here to tell you, like an assertion, to tell you that this shouldn't happen. All right, questions on this process. So I know for this project is probably a little frustrating, probably a little difficult. I know it's difficult. It's also hard to specify a compiler, especially when it's informal like this. But what I'm hoping the kind of skills you'll gain or the experience you'll gain is applying this stepwise method. To step back up, the reason I was going through this was to show you this stepwise approach where, it's kind of true in science as well, where nobody is there to give you the answer. So the answer is here in class. If you're working on a new project and you're doing new coding, or you're trying to solve some hard problem that, say, hasn't been solved before, you're doing research, there is no ground truth already made for you, necessarily. And so the key is to basically build your own ground truth as you go along, confirm correctness as you go along, and use the programming techniques that are given to you in the language, like functions and printing and other tools to help you confirm that the code is working piece by piece as you go along, to avoid having to debug what could be simple issues later down the road when you're implementing something complicated. So if you were just doing this on, say, a big 100-line simple C program, there may be all sorts of other pieces of your compiler that you haven't even written yet. So if you remember back in the first lecture, one of the goals, kind of ulterior goals that I had for this class was to get you to think not like programming like this, where you say, I'm just going to leave the whole program open. Anything can be tested. And then you end up with an implementation that has what are actually bugs everywhere, but you don't think of them as bugs, you're just thinking in your head, well, I didn't implement that yet. But your test cases are breaking for reasons unrelated to what you're coding. And so this stepwise refinement approach is one instance of doing this, where you break the problem down into specific pieces that you can test individually. And that's even down to the individual. And so in the Nicholas Wirth paper, he even goes to the extreme of just individual statements in the program, making a specification for that one statement to say, if I'm assigning this variable, I expect the input to be the variable I'm assigning and the output to be the variable I'm assigning to. Because there's even, if we're tired or we're coding quickly, you can even make a mistake there, like a typo. Compiler may catch that, but it may not. Maybe you use the wrong variable there, and you just made a little mistake. You can treat that statement as like a function that has its own input and output, and test it just like you would a function. Print out its input, print out its output, and use test cases to confirm that it is what you expect. And sure, you won't necessarily know all the input-output specifications, but for the example we just looked at, surely you can check that the sub-expression is A, and it's hard in C because you have to go through these structs. But you can confirm that without knowing all the inputs to simple C. And so this is, I think this is the best illustration, or a good illustration in this class of programming this way. programming, and defensive programming is one sort of term for this sort of. But I don't know, I'm kind of mixed about that because defensive programming is like, I don't know whether I made a mistake somewhere else. A sort of stronger version of this is like correct by construction, where I made this so correct, I analyzed it, I went through the specification, I stepped through each line of code, and I tested it to the point where I have a very strong guarantee that this works. And then I don't even have to defend against it anymore. I can just assume and write an assert statement to assume that this component is using this component correctly. Yeah. Yeah, well, unit testing is an instance of this. So unit testing is basically testing each function in your program, or if you're programming with small functions. But yeah, unit testing, yeah, exactly. So all of these approaches, unit testing, proofs, correct by construction, these are all ways of breaking down the program into well-defined pieces that you can test or prove individually are correct. Yeah, so unit testing is an approach, is an automated approach for testing. If the specification is broken down into functions, then unit testing is a way to exercise those functions for well-defined and well-known inputs and outputs. Yeah, so you are effectively doing like unit testing kind of by hand here. But also what I kind of also want to show you is that you can also do this by reason. You can reason that the code is correct, and you can even write a proof that the code is correct. And there are even ways to do automated proving of code. Yeah.
Do you mind showing the code again?
Sure.
I was a little confused on the refer to the sub-expression type line to check what it is, but then when we're actually assigning the type of tree.
Okay. Let's return to the actual test case here. So this was our unary expression. That's the tree. And so this is our test case. So we expect A to be a pointer to an int here, and we expect the dereference of A to be an int. That's what we expect to see in our tree. And if we look at our tree, this is what we get. So the unary expression is the deref operator, its subexpression is an ident, and its resulting type is an int. Looking at the subexpression only, the subexpression is an ident expression, just A, and it has a pointer type, and that pointer type points to int. Make sense so far?
Can we set that in the code?
Yeah, so to tie this back to the code, we assign subexpression to be this expression, and expression was this whole unary expression. So expr is this, and sub-expression is this, or at least that's how we coded it in our example. So knowing that expression is this unary expression, and sub-expression is this, what's the relationship between sub-expression's type and expression's type? Well, what's the type of the sub-expression? It's a pointer to an int, and the type of the expression is just int. So how did we get the type of the unary expression from the sub-expression? Or at least, yeah, so this is a pointer to an int. The dereference should give us the int, the thing that's being pointed to. So where in this type structure do we get that int? Yeah. Yeah, from the child of pointer type. So the way the type structure works, the primitive types are just single nodes, and the type constructors like pointer types are trees. So the pointer type has one child, which is the type it's pointing to. And the reason it's a tree is because you can have a pointer to an int, like in C, or a pointer to a pointer to a pointer to an int. You can have a pointer to a function, which points to an int, and returns a pointer to an int. Yeah. Does that answer your question?
So what does that look like in the code?
Okay, in the code, so that's actually this last assignment here. So this was the sub-expressions type, which was a pointer type, And to get the thing it's pointing to, this is the child of it.
So that's setting the entire expression.
Yeah, this is assigning the entire expressions type, which is here, to the sub-expressions type's child. If that makes sense. So to look at it graphically, we're taking the pointer type and saying, here's the thing it's pointing to, pulling that type out, which is just an int type, and then assigning it to the expression type.
Did we also assign the sub-expression type? Like, did we
So who assigned the sub-expression type, or at least in our type checker, who's responsible for assigning the sub-expression type, or how did it get assigned?
Okay.
So if we look at our comments, we left our comments in here. The first thing was to type check the operand. And to type check the operand, we just recursively called the expression type checker. And that gave us the type. So another good reason to have, you can actually just write comments first. There's no rule that says you have to comment after the fact. Actually, it's easier to write comments first. Yeah. Oh, you mean this? No. No, it's just a variable assignment. But the benefit of using variable assignments is that you can clearly delineate the steps in your program. And your compiler can optimize away any additional overhead of copying memory around. Like, the compiler will not literally do this. It'll do the replacement for you. So there's no danger at all in breaking things down into clearly defined steps and giving them clearly defined names. In fact, it'll help you doing that. And the compiler will handle it for you. It'll optimize that away. Okay, questions on this? Who's finished the type checker? Who's halfway done the type checker? Who's really struggling with the type checker? Not too bad. Okay. Because it is due tonight, right? Yeah.
I know that in the beginning, like in the syllabus, it says if by the end of the semester you have a complete compiler, you'll get an extra 2%.
Yeah.
If you turn in one of the projects late, but then go and fix it,
Yeah.
and you lose that 2%, you'll still get the
Yeah.
It's not like every project it can be done by the deadline.
Right. No, they don't. Yeah. By just all of them by the end of the semester. Yeah. Yeah.
So technically there's no late penalty, or?
There is a late penalty. It's just very, very small. The late penalty is like 2 points, 2% of the total grade. Well, for the whole, you get one of the 2% back. So I guess there's like 3 lates, 6 points, and then like 2. So I guess the worst case you'd lose, the worst case you'd lose 6 points. And if you're late with everything and turn everything in, you'd lose 4 points, I guess. I hope that's small. I mean, I wanted to make it not 0 because then some people need the structure of like, I need this deadline. But I also don't want to penalize people for trying again and failing. So that's what I settled on before. But if you actually made a genuine effort and you actually like got things working, then that's really the main goal here. Is I want you to like get this working. And our tests are going to be pretty light, and I've simplified the back end a little bit so some of the stuff should be easier. Okay, but it seems like people are actually pretty good on the type checker, I think. Okay, yeah.
Not to finish, it was rough.
It was rough, yeah. I know it's rough. Use this approach for the back end, little by little, yeah.
I also I finished it and it's funny because for the 4 test cases that aren't graded, I passed 3 out of them. But Sudoku, I just wouldn't be able to do small tests.
At all.
Yeah, and it's weird.
Well, so we're not grading Sudoku because of the array issue, but
It's weird though because my binary, I was looking at my binary expressions and it should work because my binary ops, my math run passed. And I checked all the individual functions and I tested them and I tested outside of that
Might be a bigger program. So one strategy is to delete stuff from Sudoku until your code stops breaking. And that'll tell you what line of code is breaking it. Just like with this. This is called delta debugging, where you can actually have your code effectively, still making it valid, test it. If it's still there, it's just like binary search. You just can find where, minimize the test case. There's even automated approaches to minimize test cases. And that will help you zero in into your program, and then you use the reachability technique to say, which part of the code is it being hit? Just do a print statement. And then you'll have less ambiguity about where in the code it's being broken. Yeah?
I know that you're not grading on those 4 test cases, but you did the updated versions are correct, though?
I think so. I hope so. Yeah, I think they are. Yeah, it's now type checking. Yeah.
Wait, so the extra 2% is for the 4 projects together?
Yeah, the 4 projects kind of working together.
Okay.
Yeah.
Thought it was for each one.
No, well, yeah. I mean, if you have any issues with your grade, by all means, talk to me at the end of the semester. I will have lots of office hours at the end of the semester. My goal is to make sure you guys learn something, that you actually become a better coder, really, is my hope for this class. It's kind of the main goal. All right, let's take a break and come back at 11:30, and then we'll continue on with the back end. All right. And the type checker is organized in a similar way, where we have functions that are also similarly named, where we generate code for each piece of our tree. And we're going to design these in such a way so that when we emit code for one sub-expression in our language or one statement, that it'll work correctly together with all the other generators in our language. So I reviewed functions already in our language. Let me go over, just to show that one more time. So functions, and I'll go through the actual implementation of it, how to actually do the code generation of it. But just remember that we're setting up this stack frame every time we make a function call. And and our compiler is not going to actually issue the instructions to set up. We're going to issue assembly commands that cause this memory to be set up to have this layout. So let me go to the example that I had before. I'm going to turn this back into a code generator. Looks like I introduced a bug in my code. So last time we looked at this simple function definition here in function call, where we have a function that just adds its 2 parameters together. We passed in 1 and 3. And the back end of your compiler will translate this into assembly code that we can then just compile with our existing system software. So here I'm saving it to this simple function.s, and then you can just compile it with GCC, which will call the assembler for you. So there's the output. So our function was taking 1 and 3, adding them together and returning that. And this is documented in the instructions, but the main methods, if you ever wondered where the return value goes, it's collected by the operating system and it's made available to you as the user of the operating system. You can actually get the value by using this special bash variable money sign question mark. Esoteric, I know, but that's how you can get the return value of any main method. It's meant for error reporting. Okay, so let's go through how each piece of this generated function works. Okay, so at a high level, this function just becomes a label in assembly. So we were talking about functions before, why you need the stack. In assembly, a function is just a sequence of code with a label. And so it doesn't have any of this state-saving behavior that we really want in the function. So all we do for each function is we just generate a label for it, and there's some pseudo-ops here to actually declare them. We just spit out all the code that makes up the function. And same for main. Main is just another function that has its own label. So looking back to our stack frame, what our caller does is our caller passes the parameters, it sets them into registers, and pushes them on the stack as needed. And so we can look for our function call to f here in our code to see that in action in the assembly. So this is the code here that sets up the parameters, sets the return value, and branches to f. And all of it's right here. So I'll explain probably next time after the break why we use push and pop here. But here is RDI and RSI, which are the first two registers used to pass the first two parameters of a function, RDI, RSI. So there's RDI and RSI. So there we have no stack to set up here because by this x86-64 convention, we pass them in registers. So here's the two registers being set. And we saw with GDB last time that indeed those registers are being set to 1 and 3. And here's the call. In the Intel world, call does two things. Call first pushes the return address, that is the address of the next instruction here, which is push RAX. It actually pushes that onto the stack for you, and then we'll branch to F. Afterwards, since there's no cleanup of the stack to do, there's nothing to do for the stack in the caller. So questions about this code at all? Just seeing the function call in assembly? Pretty straightforward, right? There's not much for you to do to set up the call stack in the caller. Yeah. So these are so the way our expression evaluation will work is we'll push immediate values onto the stack so that we don't have to have registers for them. And so the code before this will connect. So you can think of each of the expression generators as like Lego pieces that fit together through a convention that I'll show you that we use, a simple convention. And so at this point we can assume that all the parameters are on the stack, and then pop them off into the registers needed to pass parameters. So that's, yeah.
So pop just takes whatever is on.
Oh, yeah. Exactly, yeah. So pop, yeah, exactly. Pop takes a value off the stack and stores them in the register you give. And I'll show expressions. I don't know if I'll get to it today, but I'll show expressions how that works. So this is, by all means, not the only way to do this. A clever compiler will probably have these set up already. We'll probably have them allocated already. I mean, we'll not need to use memory to do this, but much easier on a compiler in the way that I'll show you. Let's see. Okay, so the main thing here is we just put the values in the registers, and for your project, I'm only requiring a single parameter, so you'll only ever have to use registers. If you like, by all means, try to do arbitrary numbers of parameters, but it means you have to, put the first 6 in a register and then put the rest on the stack. A little bit annoying, coding in C. But the most salient thing that the caller needs to do is just call the label that we made. For similar reasons, the return value is given also in a register in this calling convention, in the A register. Actually, it doesn't even have it here. Return value. So it's not even listed on this page, but it's in the A register that the return value is put. And so in our scheme for evaluating expressions, we always store the resulting value on the stack. So that's why we push RAX onto the stack. But I'll get to that more when I talk about the expressions. Really, the only thing you have to do is just actually do the call, which will put the return address on the stack and then branch to F. Just branch whatever address F is. Okay, so that's setting up this part of the stack, the caller, the part of the stack frame that the caller is responsible for. Here's F. Here's the whole function F. So let's just look at the call stack setup, or the stack frame setup. So I'll just delete the rest of the code for a second and just show setting up the call stack. So this is all the code that needs to be emitted in order to create and tear down the rest of the stack frame. So the rest of the stack frame has the old RBP and the local variables. So who remembers what this RBP is used for in the Intel world? Yeah.
It's the last frame you came from.
It's the last frame you frame from, exactly. So RBP, the RBP register is intended to be used to store a pointer to the stack frame. So to put this in the context of our homework, if you remember in our homework, we needed some way to store a pointer to the caller frame, some way to get back to the caller's function local state. And in the Intel world, the convention is to use the RBX register to always hold a pointer to that. That's the convention. And so in order to get back to the caller, we store the old caller's RBP, their old base pointer. So how can we do that? How can we push that onto the stack? What assembly operation do we use to push something onto the stack? Push. So the first thing we do here is we push RBP. RBP is the current caller's base pointer. So we push it onto the stack. But that now is pointing, that RBP is still pointing here. So we push it onto the stack here, but RBP is still pointing to the old function stack frame. So now we want to update RBP to point to our callee's stack frame. So the clever way to do that is to observe that the stack pointer is already pointing at the stack frame. So we just take the current stack pointer, whatever address of the current stack pointer is, which is pointing here, pointing to the frame, or pointing to the element that's holding the old RBP, and move that into RBP. We overwrite the old RBP with the new base pointer. So I think the reason, you could store this anywhere in the stack frame. It doesn't have to be at the location of the RBP, but I think they do this because it basically makes a linked list. So you can follow RBP to the previous caller's RBP, and then that address is already pointing at the caller's RBP. And so in languages like nested functions, if you want to find the stack frame of parents, then you can follow this linked list without having to do any offsets. I think that's why it's done that way. But this is just a convention. You can store it anywhere. But by this System 5 64-bit convention, this is where the old RBP is stored. So it's pushed first, and then move will update the RBP to be our current stack frame's pointer. And the next thing we need to do is to allocate space for the local variables. And so the kind of parsimonious way to do this is to just count up the number of bytes we need for the local variables, and then push them onto the stack all at once. And so we do that by using subtract. So why does it subtract and not add? Yeah. Exactly, yeah. So in the, I guess in the Intel architecture and a lot of architectures and a lot of operating systems, heaps grow up, stacks grow down from the top of memory. So yeah, that's why it's all subtraction. And so you'll see when we go to actually access, and you can see here, we can actually access the local variables as an offset from the base pointer. So the key trick here is that we can allocate memory at runtime. Like we don't know at compile time where in memory local variables are going to be, but we can always find them from the base pointer. We can always take whatever value is in the base pointer because we set it up, cleverly set it up so that it's always pointing at the stack frame. And then if we ever want to access a local variable, we just access it as an offset from RBP. So that's the main trick of this calling convention. It's okay. Sorry about that. Okay, so we set up our stack. Let's take a look. Let me just do a quick overview of how expressions are being evaluated here. So this push RBX, this is just for the convention reasons. And actually let me actually show you how this code, what the code looks like when it sets up the function. So here's the code generator for main, whenever it sees main. And it creates a symbol table which is going to hold the memory locations of our local variables. This is just some of the pseudo ops needed for the assembly file. This is code that emits the label for the function. So in this case, it's main. If you look at the assembly program, that printf is what, so we're literally just printing out assembly code. We're literally just calling like printf to spit out assembly code. And so this is what prints out the label. The declaration list, all this is going to do is add up, basically insert things into the symbol table for us. This is how we handle input parameters. We give space for them as local variables. And I've given you a function that will emit the prologue for you. It will set up this emit code that will set up the stack for you. This emit prologue will spit out these instructions. And if you want to take a look at what that looks like, it should be given to you. All it does is print out a push statement, a move statement for setting up the RBP, and it does a little math to set up the right stack size. So in this calling convention, it has to be aligned on the 16-byte boundary for reasons. I don't really know actually what they are. But in this calling convention, it has to be on a 16-byte boundary. So I've given you code to do that already, so you don't have to worry about that math. It causes seg faults if you get it wrong. And RBX is pushed because in this calling convention, the RBX register is supposed to be saved by the callee. Okay, so that's all the prologue does. So this code handles taking the input parameters. So in this case, the input parameters are argc and argv. So this is the code that takes the input parameters, and in my design of this compiler, all of the local variables, including parameters, are on the stack. And so this code here will take the input parameter, which is an RDI, and store it onto the stack. So this assembly instruction here, this style of assembly instruction, this -8 parentheses RBP, this is how you express RBP -8 in the AT&T syntax of Intel assembly. So if you want to access this memory location, the memory location that is offset by -8, This is the syntax for doing it. So what this says is take whatever value is at RBP, whatever address is there, subtract 8 from it, and then go to that memory location. So in this case, it'll take whatever value is in RDI and store it in the stack frame offset by 8. Questions on that? Does that kind of make sense? Yeah.
Why is it 8 bytes when you usually
Yeah, that's a good question. So in C, in the 64-bit implementations of C, ints are 32 bits. I just made everything 64 bits, just as a simplification, just to make it easier. Yeah, so in our language, all of the primitive types are 64 bits. So everything is 8 bytes. It just made things a little easier for me. But certainly, yeah. And this is a language design decision, right? So in C, ints don't have a fixed precision. Their precision is dependent on the architecture you're on. So I think on a 32-bit architecture, they're 16 bits, right? Does anybody know this? I think they're 16 bits on a 32-bit architecture, which makes code porting a real pain. But yeah, that's why it's 8 bytes. It's simply a design decision to make our data fields 8 bytes. You could actually store 32-bit data in here as well. You'd just be kind of wasting space. But the memory in this architecture is byte addressable, so you can access individual bytes. Although there are assumptions about word boundaries in the stack. But yeah, good question. Just an arbitrary design decision. Okay, so that's the code that. So by convention in the compiler that I'm giving you guys, we allocate space for all of the parameters as well, and then just copy the registers in there immediately. So generating code for the body. So just like with a type checker, each function is only responsible for its code construct. So main does not have to produce code for statements. It just calls out to the code generator for statements. And similarly for a return expression, we've got a code generator for expressions that we just call out to. And this will save the return expression. So just to kind of preview the convention here, just like in the type checker where we made the convention, the contract between the type checker for expressions is that whenever you type check an expression, you store the resulting type on the tree so that the parent caller has access to it. We use a similar convention here for code generation where whenever we generate code for an expression, we contract with ourselves the rule that we always push that resulting value onto the stack. So that way there's no need to communicate, there's no need to put things in registers. We just by convention say whenever we generate code for an expression, the last thing we do is store its resulting value on the stack. We push it onto the stack. And what makes this easy, the reason this makes it easy is because whenever we call a code generator for the expression, we can always get the resulting value by popping the stack immediately after calling the code generator. So this is not what professional compilers do, because that would be very memory intensive, it would be wasteful. They try to make sure things are always in registers as much as possible, but it's complicated to do that. So an easy way to do it is to just always push things onto the stack. It's kind of like, who did so you did infix to postfix, right? Who did infix to postfix? Did you do evaluation of infix? Who did evaluation of infix, where you compute the result? You did that, right? So where did you store the intermediate results? Like if you have +3, -1, 2 or something, when you compute -1, 2, where does the result go? On the stack. Yeah, stored on the stack. So we're actually doing the exact same thing here. We just use the actual machine stack and use Intel assembly instructions to push and pop from the stack. So basically we're not actually evaluating it, but we're generating code that will call push and pop. And we always have a rule that every time we generate code for an expression, the last thing is going to be a push onto the stack. So that way when we generate other code around it, it will have the guarantee that result will be on the stack and we can call pop. So that's why, at least in this compiler, we have pop here to save the return value. The Intel calling convention that we're using here, the return value is supposed to be an RAX or EAX. So that's why we're popping RAX after. I'm sorry, this is not a function call. This is just an expression. So our internal convention is to have everything pushed onto the stack. And then we have the code that emits the epilogue. So I'll just show you that real quick. it just is exactly, it's always the same for every function. It just restores the old B register, updates the old base pointer, updates the old stack pointer, updates the old base pointer, and then calls return. So it looks basically identical to the emitted code. So I've given you a series of macros here that will generate assembly for you to make it just a little easier to write code. Yeah?
So are those functions just printing the variables?
It's just printing assembly code. It's just literally printing text. So yeah, actually that segues into this. I've given you, so you could just literally put printf statements everywhere to print out this code. That's a little tedious and a little ugly, so I gave you some macros that will kind of map to the names of the assembly code that you need to emit. But yeah, as you asked, this is like literally the text that gets printed out. That looks a little hard to read. This is literally the text that's being printed out. And I just have nice spacing with like tabs and things like that. And it's a printf statement, so the parameters, it's parameterized, so you can pick a different register or a different memory address. So for instance, that instruction that copied a register's value into memory, the instruction here, this move instruction that copied a register value into memory at some offset, I've given you a macro to generate that move to offset. Where is move to offset? So I've given you a macro to do this for you. So all you have to do is give the register and the offset. And so we compute the offset ahead of time, and I'll talk about that more next time. There's another symbol to be able to store these offsets. You just allocate a different offset for each local variable. And this just generates the move from whatever register you gave it to this register indirect addressing, this parenthesized offset syntax is generated here. So it's always from RBP, so I just hard code RBP, and whatever offset you give it, it's here. Now, this is also another reason why I want to give you these macros, because the AT&T syntax for registers uses %sign, but that's kind of overloaded with printf, so you need 2 %s to escape it. It's annoying. So I thought it was a little cleaner to give you just this syntax, so you can just say the name of the register in text and then the number of the offset. And there's a whole series of these for all of the, you won't have to emit any novel assembly yourself. You can always use, you'll always be able to do it with all the macros I've given you. So push, pop. I separated all the move instructions because there's, moving constants, there's moving variables from offsets, there's moving to globals, and they're all slight variations of Intel's move opcodes. They're pretty extensive, the flexibility that you have with Intel's load and store operations, so I've just kind of hard-coded only the ones you need. All right, so I think that's probably a sufficient overview for now. I've put a reference to the Intel instruction set here. It's extremely extensive. This is not a RISC architecture by any means. And if you want to actually look into the meaning of these, you can see, you can just see how many different variations of the move instruction there are. So picking the right one is kind of a pain, so I've just basically given you hints to all those with the macros. Yeah?
Real brief,
Yeah. Yeah. Yeah, so I've given some bonus, I've listed some places where if you add that, you'll get bonus points, and I've put bonus points in the project as well. So yeah, if you finish a compiler, if you add some new stuff, you could potentially get back 9 points or something like that, 9 percentage points on your grade. So, yeah, I can talk about that more next time, but yeah, you see instructions in there that says that. All right, so Clay's officially over, so go if you need to, but let me get the last question in. Yeah. Yeah. Yes. Yeah, that would be one of the bonus ones. If you can do multiple parameters, yeah, get bonus points for that. All right, everyone, have a good break. Take care.
Sorry, I thought of more questions.
No problem.
Sorry.
Yeah, no problem.